Welcome to Unlocking Science. Our goal is to glorify God by studying and unlocking the secrets of His amazing creation. I'm your host, Mr. P. Dr. Danny Faulkner, one of our regulars. He'll be here today talking about the idea of specific heat. Now, most people probably don't know what that is. So if you think about that word, will you think this is more of a physics demonstration or a chemistry demonstration?
Yes.
Well, what do you mean by yes? You can't answer that. Come on.
Well, there's an overlap. You know, we deal with things in physics that deals with chemistry too. We use Avogadro's number and the ideal gas law.
6.022 times 10 to the 20.
So anyway, we do deal with heat and heat transfer. I know people in chemistry do as well. We're probably coming at a little different angle, but it's still the same intersection of science there. It's really cool when you can mix two.
Absolutely. So I'm more of a chemistry, biology guy, and you're more of a physics, astronomy guy. So we're going to look at this topic from both angles. Think about how the idea of specific heat. And really our focus today is on water. Water has an amazing superpower, and we're going to teach you all about that superpower today. All right. So when we think about the idea of specific heat, let's go ahead and define that for the folks watching.
Okay, it's the amount of heat required to be added or taken away from something to raise its temperature by so much or lower it so much, change in temperature. When you apply heat, like you're putting something on the stove, you have a flame or a current going through the coils, it adds heat and temperature raises. If you want to freeze things or cool them in a refrigerator or freezer, you have to pull the heat out. And so the specific heat measures the rate at which that happens.
Okay, so this is kind of a ratio unit. We've got the formula here for you on this card, okay? So more math. Now, don't be afraid of the math, but science has lots of math in it. So the little symbol C over here that you see, this indicates the value for the specific heat of the substance. The Q is a measure of the heat units that we're putting in. M is a measure of mass. And then delta T, when we use this delta symbol in science, we typically mean change in something. So this means the change in the temperature. Now, are these units always the same, Dr. Faulkner?
No, they can be quite different. In fact, your units you put down here, you put down joules for heat. And turns out we named the joule for the fellow named Joule in the 19th century, who was the first to prove that heat was a form of energy.
Yes.
And that's pretty standard, except for this kind of work, I like the calorie myself. It's a little different unit. And then in the denominator, you have grams, and when you're using calories, grams go pretty well, but generally if you're using joules, they like for you to use kilograms.
Okay.
Pretty persnickety about that many times. The temperature can be Celsius. That's usually the unit we use, rather than Fahrenheit. It doesn't matter if you use Kelvin, because the difference in temperature would be the same on that scale.
Since we're taking an absolute value of a difference, it doesn't matter if we're using Celsius or Kelvin, they're equivalent. We could also use kilojoules as the unit here.
Or kilocalories.
Kilocalories, kilograms. So all these different values can be assigned based on the things that we're using. And sometimes even different scientific disciplines will prefer one type of unit or one structure over another. So if we think about the periodic table, I've told you guys many times how beautiful I think the periodic table is. So it's got all of these different substances on it, all the different elements that we find in the world around us and in the universe. And each of these would have its own unique specific heat. And if we think about combining these in different ways, so if we take some hydrogen and some oxygen and mix it together to get water, then water as a substance, as a molecule, would have its own unique specific heat. Is there any kind of design evidence that you could think of with respect to each of these things having a unique specific heat?
Yeah, I mean, you can understand the physics of how these things come about, but I think there's design built into it. I think we're getting to the idea of water once again. Water has an amazingly high specific heat. It is one of the highest, if not the highest, specific heats. And what that means practically is it takes a lot of heat addition to heat water up, or a lot of heat extraction to cool it down. That's the reason why they say a watch pot never boils. Well, because it takes a long time to raise the temperature to the boiling point. Eventually it will boil, but it just takes a while. Most substances work pretty quickly on this front.
So here's a table we've got that compares some of the different substances. So if we think about water, and we're using the units I mentioned, joules per gram degree Celsius, water has a value of 4.186.
Now right here, that's the reason why I like calories, because for water, that is 1.
Metric system that a lot of Americans don't like to use. The calculations become a lot simpler in those areas when we're using grams and degrees Celsius and those types of things. But other ways, it's a lot easier.
And one of the things I like is the fact when you talk about calories instead of joules is I can make a quick comparison. I can look and see immediately if something is 0.10, I know specific heat of water.
Yeah.
But then if I look at here, I have to divide that into that, and that gets tricky.
Okay, so we take something like this copper pipe, something we'd commonly use to run water through. It has a specific heat of 0.385.
And that's pretty low, as
That's
you can
pretty
see.
low. So that tells me that it would gain heat very quickly.
And you can sort of test this in your own home, by the way. If you have a basement or crawl space where the pipes are exposed like that, you might want to go close to the water heater. Put your hand on the pipe 4 or 5 feet away from the water heater with hot water, and then have somebody elsewhere in the house turn on some hot water, and you'll be amazed how fast this pipe will heat up.
And you could even trace the pipe back closer and closer, and you'd probably be able to tell it gets warmer and warmer as you get
It's a little
closer to it.
experiment you can do impromptu at home.
Yep. So other substances, things like aluminum, they have a value of 0.9, so a little bit higher for a metal. Iron, that we typically think of in steel, about 0.4. Gold has a very low specific heat, 0.129. And then ethanol, ethyl alcohol, that you'd think of in types of, most rubbing alcohol is isopropyl alcohol, but it's about the same value, 2.4. And then concrete, or rocks and things like that, basically limestone things, around 0.8 or 0.9. So these different specific heat values are things that we can use to take advantage of. Now we've got a little demonstration set up here to show you how this works. So what we've got is I've got my, I just went to the wrong spot, of course.
On camera.
Cancel that.
There you go.
Okay, we've got our temperature sensor set up here. So this channel 1, the red channel here, is inside of this brick. And the other probe, channel 2, is set up inside of the water. It's the blue. Now, we're going to turn this hot plate on, and we're going to get about the same temperature coming from the hot plate. So we're trying to control the variables in this experiment. The heat's the same, the mass of these substances is the same. I weighed this block, it weighs about 200 grams, and so I got about 200 milliliters of water to compare that. So we're going to turn this on, and we're going to watch what happens to the temperature.
Maybe the kids might want to kind of anticipate what it would be. If you look back here at the water, its specific heat's pretty high, it's over 4. And yet we said concrete, it's going to be close to brick, is 0.8. That's about 1/4 of what the water is. So kids, what do you think will happen? If we put the same amount of heat in these things with the same amount of mass, which one's going to heat up faster?
Yeah, so we started out about the same temperature. They've been sitting at room temperature. There's a little bit of variation in them, about they were about 0.6 of a degree off. So as we think about
Got the heat on
some
yet?
heat on.
I don't think you have it
it's
on.
starting to get warm, I think.
It's on?
Yeah,
Okay.
it's on. The light came on.
All right.
Okay, so we're going to let this run for just a minute. And when we start to notice something happening here, we'll call the camera back and check that out.
It'll take a few minutes for the heat to work its way from the hot plate into the hot plate and then into the water and into the brick.
So as we think about this concept, different substances are going to have different specific heats. And that's going to give them different physical properties, and we can take advantage of those physical properties in lots of different circumstances and situations. You mentioned water earlier as being very unique, as having this very high specific heat. Why is that so important for us here on the Earth?
Well, for one thing, we can use it for heating systems. Some buildings are heated with hot water, and if you put heat into that, it will hold it for a very long time.
Okay, so a boiler system that's used as a heating system.
And my dad had a house for a while that had wasn't steam heat; it was hot water heat pumping through, and it really worked very efficiently. We used it for cooling as well. You know, in your car, you have pipes running through your car and a radiator. and it takes waste heat from the engine, sends it to the radiator. And it's very efficient because, again, the high specific heat, when you heat the water up a little bit, it takes a huge amount of heat away from the engine. Without that, your engine would melt and burn up.
So that radiator is often made out of aluminum and other metals that have a very low specific heat and
there, but still cold water can chill things very nicely.
Yeah. All right, go ahead and bring the camera in here. We can already start to see a little bit of difference. So our upper channel was the brick. We started both of these around 23 degrees, and you can see the brick has already gone up almost 3 degrees, and you can see it climbing.
It's going about 1/10 of a Celsius every second.
And you'll notice the water down at the as quickly.
And that's because the high specific heat of water, it takes a lot of heat absorption to change its temperature.
Now, we're not directly measuring the amount of heat energy that's coming out of this hot plate, but we know that it's common to both of them. We've controlled that variable. And we could do a calculation by measuring this temperature change, and we could actually approximate the specific heat of each of those, and we could figure out how much energy we've actually gained in each of these substances by just using these equations that we took over here, rearranging them a little bit.
And you'd find them be about the same, but the temperature difference would be different.
The temperature difference is going to be quite a bit different. Okay, so when we think about water also, our planet has a lot of water on it, doesn't it?
70%.
Okay, so how does that help our planet stabilize things and sustain the life that we have here?
Well, the water holds in the heat and holds in the cold both.
Heat coming from the sun as the primary source.
And the best example I can think of, you may have learned this in geography class, is what we call the Gulf Stream. It flows out of the Gulf of Mexico up the east coast of the United States and then across the Atlantic. And then it hits northern Europe, and Scandinavia, northern Europe are kept pretty warm, but particularly the British Isles. It's surrounded by water, the North Sea and the Atlantic and the Irish Sea and the English Channel. And that water is, in the summer at least, and on into the fall, is actually warmer than it would be otherwise. And particularly in the winter, it's warmer. And so it heats the air, and the air doesn't have a very high specific heat, so it heats very quickly. And so the British Isles are kept very mild, very warm. I've been to England in the late autumn, and it's quite mild. It never gets really cold in England, never gets really hot in the summer, because that surrounded by waters and a large island, it keeps it moderated. If you went to the same latitude in Canada, like around James Bay and Hudson Bay, it'd be amazing. There aren't any trees that grow there because it's too cold, because you're sitting in all this land. And that has a big effect upon coastal regions. Chicago, they give 4 temperatures there. They give usually O'Hare, which is the airport that's inland quite a bit, Midway, which is not so far inland, and then the studio downtown, and then a few blocks away right on the lakefront. And in the winter, the temperatures can be 20 degrees difference. It's always warmer on the lakefront than the cold winter days. In the summer, it can be 20 degrees cooler. It can be like 72 degrees at the lakefront, and it can be 90 at O'Hare. So that's the situation. If you live in a coastal region, it stays milder there, warmer in the winter, cooler in the summer. The biggest extremes we have in the lower 48 states, the United States, between summer and winter, are the Dakotas. Because if you look at a map or a globe, you will see that the Dakotas are the farthest place you can get from the oceans in the United States.
So there's no influence from the temperature of the water in those areas. So the water is able to hold all of that. And even as a system, the whole planet itself keeps a very stable temperature compared to other planets.
Yep. Because the Mars, for instance, has seasons, and it has a tilt, but the temperature extremes from day to night are huge. The water on their surface keeps that moderated. Now, we did a program a while back on the seasons and what causes that, and we pointed out that it's not the distance from the sun that causes the different temperatures between summer and winter. It's the amount of heat that you're absorbing because of how steep the rays are coming in and how long the sun is in the sky. What's interesting is that the Earth's orbit is not a circle, it's an ellipse. We're about 3% closer to the sun in January than we are in July. So you would think of its distance, everybody would experience worldwide summer in January and winter in July. Well, that's not true. It's almost July here, and it's definitely summer. But one of the interesting things is in the southern hemisphere, they're closest to the sun in their summer. They're farther away in their winter. You would think that would produce accentuated temperature differences between the two seasons. It doesn't.
And I bet that's because the water, the surface area of the water there helps to stabilize that and all the energy that's contained
You
there.
you look at the southern hemisphere on the globe, it's 90% water. That's northern hemisphere, like 50% water. So it acts as a thermal buffer, keeping the temperatures from getting too hot, and then it releases that temperature, that heat in the winter as well. We kind of skipped over daily things you see at a beach, like on the ocean.
We can talk about that in just a second.
All right.
Let's bring the camera in.
Oh, wow.
So we've let this run for a few minutes, and I think you can see a radical difference. The brick is already approaching 90 degrees, so that's about 67 degrees higher than we started. And the water has not heated up nearly as quickly.
Not quite.
If we start around 21, we're hitting 30 degrees.
Yeah.
So you can see just by this simple demonstration that the brick is going to heat up much more quickly than the water. Now what if we turn this off? Now this isn't going to cool down in the time we have in this show, but what if we cool this off? What's going to happen here as a result?
We're starting at 98, 99 degrees for the brick, and 55, maybe 50. It's going to take a while. It's now 100 for the brick.
It's still going to absorb a little bit from the plate.
But it's going to stop eventually. And kids, what do you think is going to happen then? Once it peaks out 102 and 56, oh, it went blank.
If the brick, there we go. If the brick heated up faster, is it going to lose its temperature, its heat faster?
And it should.
It should.
It should. But it's still going to take a while to peak. We've got thermal inertia working here.
Yes.
But see, we turned the heat off, but yet it's still gone up a good 5 degrees on the brick. That happens on the Earth too, by the way. Our average high temperatures will occur in about a month, late July, even though the maximum heating was about a week ago or just a few days ago at the time of the June solstice. Oh, here you have Claude.
Right. Oh, Claude's always trying to steal the spotlight. Taking a little bath. We'll put Claude back around there. So we talked a second ago about the idea of differential temperatures in bodies of water. So here, what we've got is a situation we'd have with an island or even a coastal area would do basically the same thing. So if this rock, this is a limestone rock, if it were heating with the sun's rays shining down on it, and the water that's surrounding it were also being heated by the same sun, so similar to the situation we've got set up here, then this rock would absorb the heat more quickly.
That's right, because its specific heat is quite a bit less than water. So.
Okay, about 4 times less. So it's going to absorb the energy of the sun more quickly, and it's going to get hot. Subsequently, the air mass that's right next to the rock is going to then warm up. There's a transfer of heat from the rock to the air. And as the air is heated, it's going to become less dense and rise. If this air is rising here, it's going to pull air in off of the water surface over here. And in the mornings, as the sun is heating up the rock and the water, you're going to get onshore winds. Okay? It's often called a sea breeze because the breeze is coming from the sea.
And then eventually what will happen, the air rises and it cools and it goes right back out and it drops back down, becomes a conveyor belt.
Yeah, we get a convection cycle, we call that, as the wind blows. But then the sun's going to go down and we're not adding energy to that system, and the reverse is going to happen. The water is going to hold its temperature longer, the rock is going to cool off quicker, and so we're going to get the reverse cycle. The air mass over the water is going to be a lower pressure, and so or a higher pressure, it's going to rise compared to this, and we're going to get offshore winds in the evening.
What happens is the land cools and it sinks here and reverses that process. It takes a little while. You know, I've spent some time in Southern California in the summer, San Diego particularly, and it's amazing. In the summer, it can get very hot inland. You go a few miles inland, it can be 100 degrees out there. But by dinner time, if you want to go out, you better take a jacket with you because if it starts reversing, and in the morning, it can be in the 50s.
Yeah, and it's going to draw that cooler air from up in the mountains back down and reverse that.
And then it goes back and forth, and the fog comes in, fog goes out. It's really kind of cool.
Surfers take advantage of this because the better breaking waves are going to happen in the evening when there's an offshore wind that will help roll the waves and break them over. So surfers prefer surfing in the evening with those offshore winds. If you have an onshore wind, it's not going to tend to stall, it's going to flatten the waves out and they're not going to surf as well. So they would understand those differences and try to interact with those things as well. So surfers do science?
Maybe they don't know why, but they know it works.
They know
There's a
it
principle
works.
behind it, though.
Absolutely. Okay. So we think about some other examples of how we take advantage of this in the world around us. You've got a spoon over there.
Oh, yeah. This is a steel spoon. Most spoons like this are. And if I put it into some hot water, it's not, but if I put it in and talked about is conductivity.
Okay, yeah.
But metals tend to conduct heat very well and electricity.
Sure.
And so what will happen is the heat will flow through this thing. And notice there's a handle on here. It's made out of plastic and a little metal on it, but it's not making contact with that. And that's a good reason because that conductivity will go through it. Have you ever made a mistake of using a steel spoon in hot water?
I'll leave it, it's a slotted one, I'll leave it in the spaghetti noodles or something sitting against the edge of the pan, and then you go to grab that handle.
And you'll let go in a
you'll
hurry.
let go very quickly because God's given us that protective mechanism.
So
to
they
help
usually
us.
put, even though you make, if you have a plastic or wooden spoon, it's better because you don't need a handle. If you go look at another thing you can do, investigate, go ask your mom first, but go to your kitchen drawer, open it up where she keeps the big spoons and stuff. You'll notice the plastic and wooden spoons will not have these handles, but the metal ones will. Science again.
Yeah, and if you use different types of pots and pans to cook with,
Handles.
we actually take advantage of that on the handles.
Cast iron skillets never have those. You better
Yes.
pick a pot holder to pick those
Yes,
up.
absolutely. We'll use copper to coat the bottom of pans because copper is a very good heat conductor and it has that low specific heat, so it's going to grab that heat very quickly from the burner, and then it's going to heat up that iron or aluminum pan. So different pans are designed in different ways to grab that heat and control that heat. Have you ever been inside of a greenhouse?
A few times.
Okay. At the greenhouse we had when I was in college at Montana State in Billings, we had these giant water barrels inside of the building. And one day I decided I was just going to go water some of my plants using the water in the barrels. And Dr. Khalil got upset with me for removing the water from the barrels. And I didn't understand why. I just thought I was getting some water that was close to my plants. But she explained to me they put those big barrels inside of the greenhouse in that cold climate in Montana, and that helps to absorb the heat energy and it helps to regulate the temperature through the night. So the heat that's absorbed by the water in those barrels will be slowly released overnight as the temperature drops outside, and you won't get the radical temperature swings.
They don't actually heat the water, though. It's
No.
just solar heating during the
Yep.
daytime.
It heats up, so just like we talked about, the whole earth follows that same principle. So we can take advantage of these things that God has designed, and we can use them to create and do work around us in a way that gives us benefit. And that's why I get so excited about studying God's creation, because it's so useful and so helpful to us in so many ways.
Yep.
All right, we hope you guys learned a little bit about specific heat. Our hands-on activity that we'll be broadcasting on Friday is actually going to be an experiment that you can do to demonstrate this principle of specific heat around the house. So we hope you'll join us for that. And until we see you next time, get out and explore God's amazing creation.